Just realised it says introduction there, that's the wrong thing. Let me write it live. Video compression. There you go. Fixed it. Cool, so looking at video compression today. Now, we've kind of mentioned a little bit of this in the first lecture with this whole thing, how this affects the world. So how video compression and all these compression systems really make a difference to the way the world works. Video is the most important thing to compress because it's the massivest one, basically. And it's the one that we still really wouldn't have a solution to unless we had compression. So we still wouldn't be able to do this. We could, for instance, still fling around completely uncompressed audio. And we did that with CDs, you know, that was a possible thing that we could do. And that's not too bad. And obviously images are very similar too. You could fling around uncompressed images if you want to. But video is so goddamn huge that it really requires compression to work. So as an example, if you had a 1920 by 1080 full HD video, and it was 24-bit color, standard decent size color, at 30 frames per second, it would be 1.5 gigs per second, which means a 60-second video would be roughly 90 gigabytes in size. Stupid. You know, that would be really chiseling into the file sizes of all of the computers we have, and we wouldn't really be able to store it very often. It would be very much contained only within sort of TV stations and stuff like that. It wouldn't be the kind of thing that we could just manage. You know, it wouldn't be available to consumers, basically. It would only be a professional thing. And fiber connections in the UK, the average speed of the internet in the UK is roughly something like 200 megabits per second now, which is relatively okay. Lots of people obviously have fiber that goes up to about gigabit, some 2 gigabit connections in the UK these days. But, you know, fiber connections most of the time are only up to about 900 or 1 gigabit, so you wouldn't be able to even stream one video source without compression. So it's a massive deal. Like, compressing video is the piece of magic that really allows a lot of our media world to happen, all the TV and stuff that we watch. So we've been talking about trying to find these redundancies, or like chunks of data that we want to try and remove, or things that we can forget about in order to make savings on all this different media. What's the big redundancy you can think of when it comes to moving images? Anyone have any idea?
They change a lot.
They change a lot? Or not a lot?
Well, sometimes it doesn't change a lot, and sometimes it does.
Yeah, so the idea there is that between frames, there might not be a lot of difference. So here's an example. So what we could do, instead of sending every single image, we could just send a difference frame instead. Now, the stuff I've got here, you can see the blocks on that. It's all compressed stuff. Again, I didn't have any raw images that were very useful, or raw video, sorry, stored on my PC that would be very good for this. So all of the examples I've got are unfortunately quite heavily compressed, and you can see heavy compression artifacts in all of them. That's just part of what we're going to look at today. It's such a shame. So, but here you can see there is 2 frames, if I go backwards and forwards, 2 frames of video, and you can see there's not a lot of difference between them. So in principle, instead of sending an entire frame there, that's the first frame, that's the second, instead of sending that entire frame, well, maybe I just send the differences. And if I sent just a difference frame, it would look like this. And you can see that the differences are basically the stuff that's happening around this guy here, and then you can hardly see it in this room because it's a bit bright, but there is the hand. Basically, it's the hand moving on the cat, and a bit of cat difference. Should we do this? There you go. So, and there's your difference frame. So you can obviously see if you were sending that as a frame, as your first one, and then you sent that as your second frame, this is very easily to be compressed. Yeah. Now, the way this actually works in real terms is that it's not actually an image you're sending. So this is a bit of a contrived example. You're sending kind of data, like metadata about the frame for it to build it back up. But in principle, you can see how that's a lot less information, a lot easier to compress. So you can send difference frames. We can send not an entire frame. We can just send the difference between one frame and the next frame, and then it can rebuild it from those differences. Now the question then is, will this always work? Now here you can see there's not a lot of difference there. You can see the background stays mainly static. There is some movement in the background, especially in the compression noise, annoyingly. But as a bit of a spoiler, I don't know if you've seen Alien, this is a shot where it's done with like a Steadicam. So while it is steady, there is a bit of floaty, noisy stuff going on in the background. And the rest of the scene isn't necessarily like that. The rest of the scene is moving around all the characters. It basically pans around the table, or whatever the term is for going left and right. People always get upset when you say pan, don't they? Dollies or whatever, trucks, yeah, I don't know, the words. So instead of doing that, or as well as doing that, what we can do is, as well as doing that, is we can send some information about how the pixels have moved. So in this example here, this is a nice and efficient difference frame. But if my frame was very different, or if the whole frame is moving, you're essentially sending all the pixels again because there's so much difference in it. So if this is moving, well, I'll show you the two frames in a minute. I've got something in Photoshop, we can have a look at it. And basically what's happening there is it's moving, the whole frame is moving because the camera is moving around the characters. And then you've got loads and loads of differences because each individual pixel is different all the time, and therefore it's just sending a whole frame again. What you can do instead, or as well as that, is do something called motion vectors. So what you would do is break this down into 16 by 16 blocks. So each of these parts of the image will be broken down into 16 blocks. It would analyze the two frames and it would say, right, that chunk of blocks there looks like it moves just a few pixels over this way. You send that information first so that all of those pixels, all those blocks can be moved to their destinations where it kind of conceivably looks like it's moved to, and then send a difference frame on top. So you send the difference vectors, the motion vectors, so moving those 16 block macro blocks, and then you send the difference frame after that prediction, which makes the difference frame closer, so less of a difference. Like I say, I've got a demo in Photoshop that I put together here. So here you can see it's that same frame. Now here is frame number 2. And you can see that we are moving quite a lot there. You see how, yes, there's not a lot of difference to you and I, but in terms of each individual pixel, if you select a location, like here, then you're moving quite a lot away from that location. The pixel values at that particular location are changing quite a bit. So motion vectors allow us to get around that. So the first difference frame would look something like this. And so you can see that there's quite a lot there. There's still quite a lot of black pixels where nothing's really happened, but there will also be shades of grey in here. So there will be things that need to be transmitted or changed. But you can see these like markings on the wall have traveled with us because they've moved, and all of this crap on the table here has moved. Obviously there's a lot of movement here for the guy's hand because he's moving his hand up during this bit. And there's obviously some movement in the characters as well. But generally speaking, you're sending kind of the whole frame again. There's too much detail in this. So what we can do instead of sending that difference frame, we can reposition the second frame. So instead of the second frame being here, moving like this, we would send motion vectors, which essentially reposition it. That's the difference. If we send motion vectors and predict that movement, it basically gives us that much difference. And then our new difference frame looks like that. And you can see that it's only the guy's hand moving and someone moving here makes the difference frame smaller, basically. So we can send motion vectors, which again breaks those things down into 16 by 16 blocks, moves those 16 by 16 blocks according to a vector or a vector pattern. And that allows us to predict frames, and we call these p-frames, predictive frames. So we predict their movement, then we send the difference between the predicted output and the original frame. So that gives us this idea, right? We've got different types of frames we're playing with now. They're not all just a load of JPEGs in a row. We can do that. We can do something called motion JPEG, where we just have a load of JPEGs in a row, and that's a real high quality video. Well, instead of doing that, we have an iframe, which is a full frame. So it's kind of what we call a keyframe or an intra-coded frame. That frame is one that is coded only as an image. It's got no temporal or directional coding at all. So every now and then you'll get an iframe. That frame will be a full quality image. And then basically for a short time after that, all of the frames are based off of that original image. You're just sending differences to that original image. So you send an iframe, an interframe, sorry, an intraframe, because it's intraframe coded, it means it's only intrinsic to itself. And then you send p frames, and they're predicted, and they're the ones with the motion vectors and the difference. Yeah? So you send an iframe, and then a series of p frames, an iframe, and a series of p frames in principle. Which is why, have you ever seen it on TV where sometimes there's things that happen that maybe it starts to lose quality and then suddenly it goes bang and jumps up again? You ever seen that? Especially if there's lots of like high frequency detail on the screen, lots of chaotic stuff. Sometimes it happens a lot with, I saw once the credits moving, because they're moving and they were happening okay, but then it was over some water with loads of high frequency waves and stuff. It was really like chaos on the background. And it couldn't code that because it couldn't predict the motion of it. And then you'd see it turn to shit, basically, and then it would go bang, and it would look good again because it sent another iframe, and then it would go bad again, bang, and it would get worse, and then you can just kind of see it pulsing. So it's doing that because it's sending an iframe every now and then, basically. Now there's one more type of frames, which are called B frames. Those frames are bidirectional. So what you basically do is you have iframes, which are your full frames, your full quality ones. You have your predicted frames, your p frames. And then in between those, you have these other intermediate frames, which will look both ways. They will generate a difference frame for both sides of the direction that they're looking, and then it will only pick the one that's got the smallest difference. Kind of makes sense. So instead of you constantly having p frames that are based on one original frame, you have these b frames in between that will say, right, I'm going to look towards the p frame, and I'm going to look backwards towards whatever's behind me, and whichever one gives me the smallest difference, I'll keep that one, and that will be my frame. And that will mean that it's smallest to compress, and it also means that the amount of error that we'll be sending will be smaller, and the quality will be therefore higher. So putting these things all together, you end up with something called a GOP, a group of pictures. So we have our iframes. So here is an iframe, here is another iframe. So these may be a whole series of maybe 10 frames apart, something like that, in principle. They kind of bookend our GOP, our group of pictures. In between there, you'll have a prediction frame, so a predicted frame that will sit in the middle, and it will basically be the difference between those two frames in the middle. Or it will be based on the previous frame. So this particular P frame will be based on that frame, and it will show the differences that it will need to change in order to get here. And then in between those, so this is what we call forward prediction, only goes in the forward direction. So P frames are only forward predicted. In between those, we have a bunch of B frames, which are bidirectional. So these ones will look and say, right, if I'm to code the difference between this one or this one, which one's the smallest error, and it will pick that and just encode that. It will say, look, I've looked forward to the next frame, and it's the difference between me and the next frame. And those can go both ways. That's what I'm trying to say with that. That makes sense, roughly? Yeah. So you can see what might be the issue with this, right? This is now a series of frames, but they are not linear. If we were to decode this from this point forwards, well, sometimes we'd be decoding frames then. We'll ask this one about what it needs to be, and it will give me the differences between it and the next frame along, which I haven't decoded yet. So GOPs, groups of pictures, have to be decoded all as one chunk. Which is why you may have been frustrated in the past if you've done things like video editing and all that kind of stuff. You have to bring in these things, and it has to sit there and decode and render and all that kind of stuff. Because what it's doing is it's working out these big chunks of pictures. And then if you do something like say, oh, I want those frames and not those ones, then it has to re-render that and think it through, which is why it takes a lot of processing power. Again, it's also why sometimes you see the quality sort of drift up and down when you're watching particularly things that have got lots of spatial information in them. So things that have got lots of high frequency detail, like confetti and waves and all that kind of stuff. Sometimes you see it get blocky and then fix itself, and get blocky and fix itself. And also it's why you get this kind of effect happening. So this data moshing, this idea, comes from, it's kind of a stylistic thing that people do now for fun, like as video editors. But it's something that can happen by accident, and you've probably seen this happen. Have you ever seen this? Like weird stuff happen? Where if you're watching a stream and you lose your iframe, then the next frame that comes along will just be the difference between that and whatever happened before it. So what can happen is when you're coding a video, the the encoder will sit there and it will wait and it will look for broad changes. If there's way too much difference in a difference frame, it will put a new iframe in there. And that happens automatically when you do things like jump cuts to different places. So if you've got a live stream going on and it jump cuts to something else, a new fresh iframe will be the first frame out, and you'll have a decent, sets up the quality of that scene. If you lose that frame, then you'll just have all the differences thereafter of the frame that happened before it. And you may have seen like data moshing and that kind of stuff. And we're going to have a little look at this today. There's some example video on the Sol page, and there's a program that we can use to do some of this. That's about it. So this is video compression, right? So this is the state of play where we were when we got up to about what we call MPEG-2. So MPEG video is essentially the moving version of JPEG. It uses JPEG compression for its iframes. And then after that, it uses these techniques, both motion vectors and difference frames, in order to give us redundancy that makes videos smaller. There are further things that happened after this, which makes it even smaller again. You may have heard of H.264, H.265, those new things. Those things are more processor intensive than this, but they're also higher quality and better compression. And we'll look at those next week. But you can kind of see why video editing and video compression takes up so much space. Because all you're getting is all these difference frames. It has to look at loads of differences. It has to determine which ones are smaller and bigger. So it has to calculate loads and loads of thousands of frames when you're encoding video. And then it has to make decisions about which frames are smaller for those bidirectional frames. So there's quite a lot of decision making that has to go on inside an MPEG coder. But that's essentially how it works. So now we're going to look at some practical activities. So if you look on the Sol page now,